The first structural element we will produce a force displacement relation for is an axial loaded member. Take this generic rod with a uniform cross-section and length L. If we apply an axial load P to this rod, it will deform. It will elongate by a given displacement, which we will denote as a lowercase delta. Before we can apply Hooke's law, we need to establish a local coordinate system for our rod. We will do so by aligning the x-axis with the axis of the rod. The directions of the y and z axis do not matter as much due to the axisymmetric nature of the problem, so we will just draw them as shown here. We can now look at Hooke's law in relation to our problem. All loading in our problem is along the axis of the rod, and there are no constraints on deformation due to the Poisson effect. As a result, there will be no stresses in either the y or the z directions. We are also not considering a temperature change at this time, so delta T also reduces to 0. Hooke's law for this problem can then be simplified as follows. We also know that axial loading produces a state of uniform stress and strain, as long as we are sufficiently far away from the boundary conditions according to Saint-Venant's principle. Integration of the stress and strain state become trivial when they are both uniform, resulting in the following two equations. If we substitute the results from integrating our stress and strain distributions into our simplified Hooke's law, we get the following relationship. Rearranging this in terms of deformation, we obtain that delta is equal to P times L divided by E times A. We now have our first force displacement relationship. In developing the force displacement relationship for an axial loaded member, such as the tensile rod shown here, we established that the deformation and the resulting stress distribution due to the resultant tensile load P are both uniform. But in doing so, we actually cheated a little. We only looked at the deformation far away from any point of load application. Why does this matter? We'll take a closer look at the point of load application in our axial rod. We simply have the end of the structure drawn with a resultant force P indicated. This is easy to draw, but is in no way an accurate representation of the boundary conditions of a real axial loaded member. There are numerous ways of introducing load into real structures. In the case of our rod, one of the ends could be built into a larger, relatively rigid structure, while the other end may have load introduced via pin bearing through a pin connection to another structure. More complex boundary conditions involving two or more fasteners could also be conceived. Looking at each of these boundary conditions, it should be obvious that they will not all behave the same locally at the connection. If we take a closer look at the built-in end of the rod, it is easy to see that this type of boundary condition locally constrains the lateral deformation of the rod. This restriction and deformation will result in shear stresses locally that eventually redistribute to a state of uniform normal stress as you move away from the boundary condition. Similarly, for the pin connection end of the rod, load introduction occurs through the pin, thus stresses in the rod are initially concentrated around that pin and have to flow around the pin hole before they can redistribute into a more uniform stress state further along the rod. First observed by the French scientist Barry de Saint-Venant, this observation is referred to as Saint-Venant's principle. It states that at a distance sufficiently removed from a boundary condition, the stress in a structure will be the same for any boundary condition that produces an equivalent resultant load. Looking at a typical engineering problem then, we are faced with having a simplified force-displacement relationship that we can apply to the structure, but also the knowledge that there is a region within the structure where that relationship is not really correct. We can of course ignore the influence of the boundary conditions and calculate a deflection using this force-displacement relationship, but we should have some way to assess if neglecting this influence is acceptable. In the problem shown here, we can highlight a length of the beam influenced by each of the two boundary conditions and denote the length of these regions as k. The question becomes, how big is k? It turns out that the answer to that question is not entirely straightforward and can depend a lot on the type of constraint provided by the particular boundary condition. However, a general rule of thumb is that the length k is equal to the largest cross-sectional dimension. So if the beam shown here had a rectangular cross-section, of width A and height B, then K would be approximately equal to B. Add a bit of engineering judgment with this rule of thumb, and you may just be able to decide if your assumption to neglect the influence of the boundary condition is valid.